Thanks. So, yeah, Stefan Biene. I'm actually happy to have so many people here, so thanks for coming. A couple of words about myself. I've been a Python developer and also an advocate since the early 2000s. Currently working for Scooby, which is an ebook subscription service. So pay a fixed price per month and you get unlimited reading as much as you like. And besides that, I'm a consultant and trainer. So I give Cython trainings, also in-house. And I'm working on a couple of open source projects, from which you may know me. The most well-known two are maybe LXML and Cython, Looper, and a couple of others. You'll find them on the page. Okay, so Cython is used a lot in big data applications, and so I would like to give you a bit of background about what we're doing at Scooby. As I said, it's an ebook subscription service, and we actually have a very large catalog. So there's more than 130,000 publisher titles, and it's actual publisher titles, not like self-publishing something. And that's all books that are available to everyone, every subscriber, anywhere, anytime. You can just click on a book and read it. And once you have a catalog of that size, it becomes kind of tricky to keep it navigable. Okay, so it becomes difficult for people to find their books, find the books they want to read, and so that's the problem we're faced with. And so the question is, how do I find my next book, right? So there's a lot of stuff you can do. You can have recommendations, editorial recommendations, but they don't really scale to large user bases. Personal recommendations, you can crowdsource that, and certainly you're trying to automate a lot of stuff. So you can do similarity search between users, between books, data mining, and so that's a major thing that we're currently working on. And that's where you come into play. You can actually help us make our book lovers happy because we're hiring. Okay, so go to that page, find a job, and come and join us, and talk to me in the recruiting session, for example. So for the actual topic of the talk, so the topic is Cython, which is, well, what is Cython? It's a couple of things. First of all, it's an open source project. You can find it on Cython.org. It's a Python compiler. It's almost a Python compiler. So it translates Python to C plus C API calls. And it features static code optimization for you. It's actually more than that, in that it's an extended Python language, which allows you to write fast extension modules for CPython without resorting down to C and writing C API calls yourself. And it's a very nice way for interfacing Python with C and C++ libraries. And over the years, so Cython is actually a relatively old project. It was originally forked from Pyrex. Who of you knows Pyrex? Yeah, a couple of people, okay. So Pyrex was a project that was begun by Greg Ewing somewhere around the 2000s. And in 2007, Rod Bradshaw and I forked Pyrex, which had kind of come to a certain stall at the time, and founded the Cython project. And since then, we had a humongous success and huge rise in our user base. And so over the time, it's really become a major pillar of the Python ecosystem, especially the scientific Python ecosystem, but it's more general than that. So by now, there are like tons of Cython code out there. And it's kind of a technology enabler. So as a programming language, it really helps people to get their job done. So how do you use Cython? So this talk is kind of split into two parts. Okay, so one is a general introduction. I'm going to tell you a bit about the surroundings and stuff and how it works in the surface. And then I'll show you a couple of examples afterwards. So in order to use Cython, what you do is you write Python code, or Cython code, as I'll explain later. Cython then translates this into C code. So you need a C compiler. to build a shared library for CPython, and then you can just import it and work with it there. So as you can see, there's an additional hurdle compared to like writing Python code, importing it, done, right? So you need a compile and build step in between. So let's compile some Python code. And it's just a stupid little example. So we have a class here, an init method, some method that gets a. So basically the idea is you has a function in, and then you call it from this method here. And that's what we do down here. We instantiate the class, and then we call this method, make the function be called a couple of times, and that's it. So really stupid code. Just a couple of lines of Python code. And when you run it through Python, it'll spit out a C file of about 3,300 lines of code. Okay? That sounds huge in comparison. So in order to get there, it's actually quite simple. We have a script, Cythonize, so you can just say Cythonize -i built in place I. Cythonize -i in your worker file, your Python script, and then it's just going to translate it. It's going to translate it to C, and then it'll build your extension for you. And then you can, as I said, import it and work with it. So why is that so large? In these 3,000 lines of code, there are lots of portability defines. So lots of stuff that says, if the CPython version you're compiling against is this, then optimize something in a different way than for different CPython versions. Very often that's the case for Python 3 and Python 2 differences, but also for new features that came in your CPython versions. So your code will actually adapt to the CPython version you're currently building it against. And if it's a newer CPython version which has a certain feature, it's going to use that. Otherwise, it will just fall back to some fallback implementation. And it might be slower, but it's still going to work. Okay. The next thing we do is we copy all the original source code into C code comments. So you can actually, when you read the C file, you can actually find your entire source code in there, which makes it easier to figure out what's happening when and which source code line contributed to what, huge amount of C code. In any case, it's definitely a lot of code that you really don't want to write yourself and for which you want to use a code generator. So rewrite C so you don't have to, okay? Building the whole thing, I already showed this Cythonize script, which is really nice, but it's kind of the thing you would use for local development. And when you want to distribute your code, you'd use distutils, and you'd let distutils build the extension module for you so that users who want to install your package have no problems in building it locally and getting it all set up. We also have a helper for that. So basically what you do is you would import the Cythonize function, after which the Cythonize script is modeled, and then you would just say Cythonize some source files, and it'll build the extension. So the metadata, the extension metadata for you, and it'll compile that for you, okay? For the more involved cases, where you want to build against external libraries, for example, so you have linkers set up and maybe include path and stuff like that, you can also use this the standard distutils way of setting up the build metadata through the extension class. You can configure it, just look it up in the distutils config. Configure it yourself and then pass that into Cythonize. Okay, and then it's just going to do the right thing for you. Okay, so I already mentioned that the code Cython generates is very portable, actually. So it generates C code that compiles with all major C and C++ compilers on all major platforms, so Linux, Mac, Windows, and some others are, well, less often tested, but general work. And in all CPython versions from 2.6 through 3.5, which is currently not released, but it's on the way. Partly also in PyPy. So PyPy has support for the C API, and we have a lot of special cases in the Cython-generated C code, which say if compiling for PyPy, then do this, otherwise do something else, which help in making it work at all in PyPy, and sometimes making it less inefficient. The language syntax of Cython itself follows Python 2.7 with lots of feature backports. So whatever comes in from Python 3, we just adopt it as long as it doesn't conflict with any Python 2 features. And if you want to have actual Python 3 syntax, you can use the usual future imports, from future import, absolute import, print function, this kind of stuff. Or you can just say, leave a compiler directive at the top of your source file, which says language level 3, and then you get Python 3 semantics for your file. For language features, so Python language features, so one of the tests we run in our continuous integration test is the CPython regression test suite of Python 2.7 and 3.5. And we're at about 98% success, so it's pretty close to full Python language coverage. What's definitely in there is like everything you would normally know, like classes, control structures, loops, try finally, so exception handling, comprehensions. We have support for async and await, which will be new in Python 3.5. Star unpacking, same thing. So this extended star unpacking, which is new in Python 3.5. So that'll all be in the next Cython release, which is currently in beta. So we have I published a beta release yesterday. So the first beta is out for version 23 of Cython. And we have support for profiling, tracing, coverage analysis, like lots of tools that help you understand, analyze your code, and make it better. Okay, a couple of deviations. We don't have frames inside of functions. Who here knows what frames are? Okay, that's definitely a clear minority. So if you never came in touch with frames, then this one usually hurt you. You'll notice frames in a couple of places, and that's tracebacks, because tracebacks are actually built on frames, but we support those. Okay, so you'll get a nice traceback from your Cython code if there's an exception being raised. That's all supported. And then there obviously, there are bugs in every piece of software, and you can find them in the bug tracker. As for speed, so Cython generates actually very efficient C code. There are many static and optimistic optimizations that it applies to your code. It generates optimized code for standard types and for many built-ins that you would use, and has static type inference within functions. Okay, so it kind of can decide what you do and when, and it understands your code in a way so it has better static knowledge about your code than the normal CPython interpreter would. One way we measure speed is with the Python benchmark suite. So there's a bunch of software packages that were assembled to measure speed of the performance of Python programs. So it's actually real-world code, including stuff like Django, some template engines. What else is in there? Some couple of computational little benchmarks. Very different. So lots of different stuff that you can run to see how fast your interpreter is. And we run that in Cython, and the problem with that is a bit that the applications that have been tested there, they're a bit outdated. Okay, many of them were written in a pre-Python 2.6 area, and that means they don't use any of the more recent Python features. It's a nice benchmark, but it's not very telling for any recent application that you would write. So in that benchmark suite, we're currently about 1.3 to 3 times, depending on the benchmark, faster than Python 3.5. And hand-tuning those benchmarks a little to make Cython generate better code for them gives you something like 4 times to 50 times. And how do you do that? Well, static type declarations. So Cython is actually a language that supports optional static typing in addition to being Python. And so in your code, you can say, you can declare variables, for example, having a certain type, and that's an extended syntax, which says cdef some type x for a variable declaration. So that's extensions to Python language, which then are only understood by the Cython compiler, not by Python. What does that do? Well, once Cython sees these declarations, it can drop your code from object operations into plain C code. Okay, so when it knows that a variable has a C integer type, for example, it can say, okay, adding a value to the variable can be done in C. Don't need to wrap any object, so that's faster. And the nice thing is that it's optional typing, so you can employ these type declarations exactly where performance matters. And that's the way we made these benchmarks way faster than what you'd get from simply compiling the Python code. Especially for computational loops, usually the speed up you get is somewhere between 100 and 1,000 times. Okay, the actual topic of today's talk is talking to native code. So I won't talk much about speedups. I will talk more about how do you connect to external libraries, how do you talk to them, how do you use C from Python. Since Cython code translates to C code, talking to native code or external code written in C or C++ is actually completely natural. Right? It's totally straightforward. And so that makes Cython a foreign function interface, but like the cool way. You can think of it as Python with C data types, and the nice thing that the compiler gives you is that these types convert back and forth from Python objects automatically for you. Okay. Cython understands pretty much all C data types and most of C++ own data types. That includes C functions, pointers, structs, arrays, and so on. And C++ classes, templates, operator overloading, and so on and so forth. Okay, and that's the end of the first part, and here's the demo. First of all, C features. Who does not know the IPython notebook or the Jupyter notebook? Okay, everyone does, that's cool. So in case there's someone here who's been working on it, so who's been contributing to the code base, thank you everyone, it's a great tool, it's wonderful. And it has Cython support. So all you really have to do is you open a Python notebook, and then you say load x Cython, which enables Cython support. And currently, as you can see, I'm using Python 3.5 and Cython 0.23 beta 1, so the newest release. And so here's an example. This is what Cython code looks like. So I start my cell here with $% Cython, which tells the Jupyter notebook that, here's the Cython cell, and please compile this for me, and then run it. And I can compile it, and it just works. And what I did here is I defined one little Python function. I defined a Python function with a typed argument. So the argument that's being accepted must be a cint. That's what I declared here. Then I have one function here, which is a cdef function, which translates into a plain C function. Okay. And then the last thing I have here is a cpdef function, which is kind of a C function with a Python wrapper. Okay, so the Python wrapper is automatically generated for you. And now I can call my Python function, which does what I want. I can call the typed Python function, which does the same thing, with the difference that if I pass in something else than an int, ABC, for example, then I get a type error, okay? And I get it on entry, so it is automatically checked for me when calling the function, okay? Then I can try to call the C function, and I'll see there's a name error, so the C function doesn't actually appear at the module interface, because it's a C function, right? It's not a Python function. But what I can call is the cpdev function, which then internally calls the C function, and that's, as I said, a C function with a wrapper around it, so the wrapper becomes visible to Python code. Okay, a bit of function JIT compiling. We have a decorator called Cython compile. So this is not a Cython cell, it's a Python cell, and you can import the Cython module and decorate a function, a Python function with a decorator, and then run that, and when you call the function, it executes, so the result is down here, it executes the compiled function for you. And you can see that because calc is not just a Python function, it's a runtime compiled function, okay? So that's how you can do, runtime compilation from within Python. Okay, calling C functions. As I said, it's entirely natural for Cython code to talk to C libraries. And the way this works is, well, we have a standard of a couple of standard declarations that we ship that includes a large part of libc, libc++, the CPython, C API, so lots of C functions that you can simply import, use, done. So the way it works in Cython is you say from libc, so the libc library, there's a module in there called math, so the math header. From libc, C import math, and then you have access to the libc math functions. And you can say math sine of pi by 2, run that, and it'll give you 1. Okay? One nice thing you can see here is I didn't just say %% Cython, I said Cython minus A. And minus A means annotate, and what I get out of it is an annotated HTML version of my source code. And that allows me to see what Cython made of my source code, okay? Because now here you can see it's exactly the source code as you saw above, but when I click on a line with a plus here in front, it'll show me the C code that it generated for it, okay? So I can see, so what it does here is it does the computation pi by 2, calls the C sine function on it, then calls a C API function on it, which converts the C double result to a Python float object. And then it calls a helper function which prints the result, because that's what it said here, right? Print the result of sine. Okay? The reason why it's a bit yellow compared to the other lines is that there's interaction with Python going on. So there's actual Python object operations here. As you can see, the result is calculated in C, but then afterwards I create a Python object from it and call the print function, and that's everything that adds up to the darkness of the yellow line here. So it's pretty dark, meaning quite an intensive Python operation going on. Okay. Memory allocation, same thing. We have the standard lib headers readily declared for you. So you can just say from libc standard lib C import malloc and free, and then you can call malloc. You have to check the result, obviously, if it's none, if it's null. Raise a memory error if it is, and otherwise, in this case, we just free it. Okay, works for me. Okay. What you should do, though, especially for little amounts of memory that you need, is use the CPython heap memory management, because that's pre-allocated memory, so it doesn't have to talk to the operating system, and it's faster for small memory areas. So what I'm doing here is I replaced malloc by pymalloc. Same thing, check the result. And here I'm assigning some values to the memory buffer that are allocated, and then do a little computation, print the result, and free the memory. Okay, important here, try finally. because even if something goes wrong here, I want to be sure that I free my memory. Up, execute it, it gives me 4. So it's adding up 1 and 3, okay? Okay, one nice little feature that came in 022, I think. So last release Python version is automatic wrapping of C functions. So here I'm C importing the math and standardlib modules from libc and take the sign and A2I function, that's actual C functions, and assign them to Python variables, okay, which makes them objects. So I can execute that, and you can look up what it does. So here, it actually calls a helper function that it generated for me, which takes the C sign function and wraps it in a Python callable for me, okay? And then it just adds it to the global module dictionary so that it becomes available to Python code. And then I can just call it from Python code. Okay, so PySign of half is apparently this, and I can take the A2I function, pass in a byte string, and it's 1 to 3. Okay, as a number. Okay, it's actually as simple as that. Okay, external libraries. Here's a bit more of an involved example because so talking to libc is nice, but it doesn't usually get you very far. Okay, so there are lots of helper functions in libc, but what you normally do is, so you want to talk to your own code. Okay, so you have some C code lying around or an external library that you want to wrap, that you want to make available for Python, use it from your Python code, and so this is how this works. So I chose Lua because I've also written a Lua wrapper for Python, which is called Lupa. So I happily copied some code from it for this presentation. So there's a Lua header file, and I copied some declarations from it, which is a state, so that holds the runtime state of the Lua runtime. I can create a new Lua runtime. There's a function for closing the Lua runtime, so for cleaning up, and I can load code into the runtime, execute it, and then, so Lua is a stack machine, and so I have some function to operate with a stack and to call a function on it and do stuff. Okay, so that's all the declarations that are needed. Important bit here is it's not complete. So the Lua header file is definitely way larger than what I've copied here, but that's all I needed. Okay, and that's all that Python needs to know. And once that's declared, I can actually just use it. Okay, so here's a function, run Lua, a Python function, and I pass some Lua code in there, and then first thing I do, I make sure it's a byte string, so I convert it to UTF-8 if it's Unicode, create a new Lua runtime, raise an error if that fails, load the code into Lua, raise a syntax error if that fails because that's activated in the Lua parser, and then get a result from that, call it, so execute the Lua code. If that fails, I just raise a runtime error saying, your code was broken, please try again. And then here's a very simple return value conversion. So I'm expecting a Lua number back, raise an exception if it happens to be not a number. Otherwise, I just convert it. So there's a helper function for converting the Lua number back to a C number, and then I return it. Okay, so that's all I need to execute Lua code in Python, or in Python in this case, to make it available for calls from Python. Okay, again, try finally. So there's a bit of cleanup after creating the runtime. The Lua runtime, I need to make sure that I properly clean up afterwards, regardless of what happens. So any exceptions shouldn't, leave a memory leak or something, or leave the runtime in memory. So I'll just clean everything up afterwards, and then I'm done. Okay? Okay. So one thing I'm doing here, now I take some Lua code and pass it into the function, and at the end I just say, so I create a function, Lua function, and then I call it at the end and return the result. Did I execute that? I didn't, okay. Well, executing that. And it gives me the 10th Fibonacci number, apparently, so it's a recursive version of Fibonacci. And I can benchmark that. That's going to give me about 5 milliseconds. And the thing I didn't mention is why does this actually work, right? So I'm using Lua code, but I'm not linking against it. Yes, I am. So what I'm saying above here is when this compiles in distutils, and I'm creating my shared library for Python, please use this include here to find the header file, use these libraries to link against. Okay, so I'm specifying that directly in my module. And now I linked against Lua 5.1. And now if I replace that by Lua JIT, which I also have installed, all I have to do is replace the include directory. So for fun, I'm just going to do that directly in my source code. I could also do that in my setup.py file. But since I have an IPython notebook, I'm just going to do it in place. Compile again, run the code again, same result, and it should be a bit faster now. Yeah, it's about twice as fast. Okay, just by replacing the Lua implementation. Okay. Okay, what else do we have? A little bit of nice syntax, C arrays. So C arrays are actually quite clumsy in C because they're basically just pointers. And sometimes C knows the length, but doesn't really care about them. So Cython knows the length of a C array, and it has better ways to deal with them. So what I'm doing here is I'm creating two C arrays of integers, length 10, A and B, and then I'm assigning to a slice. So I'm saying I have 5 values on the right, and I'm assigning that to a partial slice of the array, of the C array. Then one nice feature is I can assign by value. So C doesn't support that, right? When you assign an array to another array variable, it's just going to assign the pointers. Or it's actually going to give you an error and say you can't assign arrays. So Cython does array copying for you. It assigns by value. Very nice feature. And then I'm just assigning to the other half of the array a couple of more numbers. I can just iterate over the array by slicing it. I could iterate over the whole array by just saying for I and B. Here I'm just interested in the first 3 numbers, so I'm iterating over those, printing those, I plus 1 in this case, and then I'm returning B. So what you see here, so I created a function for it. Okay, so this is all I do. And you see the iteration actually uses a C loop over the array. Then we have here the assignment, which just translates to a memcopy, pretty straightforward code. The assignment, the partial assignment here, translates to a temporary array and a memcopy. So this is all stuff that Cython does behind your back, and it just does it right. And then when I call my function, you see the iteration here, 2, 3, 4, so iterating over the first 3 values. And then when I'm returning the array, it automatically translates to Python list, and I get the mapped Python object as a return result. Okay? Okay, I'm going to split that, and I'm just going to show you a bit of C++. Because you may not like C++, and there are lots of people who don't like C++, but it's actually really nice when used from Cython. And that's the only way I would ever use it, okay? So same thing here, load x Cython, same Cython version I'm using. And now, first I have to tell Cython that this is supposed to be compiled in C++ mode, which enables all sorts of C++ features, meaning operator overloading, meaning class support, templates, and so on. And as I said, we ship declarations with Cython that includes libc C++, including, for example, what I'm using here, the vector class. So I can just say from libccpp vector, C import the vector class. And here I'm defining a Python function with a stack allocated C++ vector object. And then I can just insert a value. There's a pushback method, whoever came up with that name, on a C++ vector class, and then I return it. What do you think that returns? Someone's saying segfault down there. Nope, because that's not what it does. It returns a list. Okay, so there's a straightforward mapping from a C++ vector to Python list. So whenever you make Python convert a C++ vector or a C++ list for you, any container it knows, it'll just convert you to a list for you, or to so a C++ map to Python dict, and so on. So you get the obvious representation in Python as a default. Okay? Okay. Another little example, a vector. The nice thing here is that Cython does the automatic memory management for you. So this is a stack allocated C++ vector, meaning it goes out of scope, it dies. Okay? All handled. You can do the same thing with an extension type. So this is the way Cython defines extension types. Anyone implemented an extension type with a C API? Okay, a couple of people. What you do basically is you take an existing extension type, copy over all that it has, because it's like this amount of C code, it's all struct definitions and stuff, and then you adapt it for your needs, because you're never going to infer that the way this works from the documentation. Okay, so you just copy it over, adapt it. In Cython, you don't need to do that. Okay, you just say cdef class, and it's done. Okay, you have an extension type. Here, I'm adding a field, so an attribute to the extension type, to the object in this case, which is a C++ vector, and that makes and that ties the memory management for the C++ type to the lifetime of the Python object. So when the object is created, it creates a C++ vector for you, and when the object dies, it will clean it up for you. Okay? Okay. So there's an add method, which just calls pushback and representation. So I can execute that. And then the wrapper is actually just implemented as wrapper of values of the C++ vector. And when I execute this, as you can see, the representation of the class becomes a list, because that's the representation of the C++ vector converted to Python object. Okay, so it just uses wrapper of list, and that's what you get. Okay. Okay, I'll just leave it at that, and yep, continue back over here. So conclusion, Cython is a tool for translated Python code to efficiency, and it's very easy to interface with external native code. As you've seen, you just write the code, and it just works. You can use it to speed up existing Python modules by concentrating on the optimization rather than a complete rewrite, which you have to do to write it in C. Avoid writing C, just do it in Cython. It allows you to write C extensions for CPython in actual Python syntax, using Python semantics, using Python language features. So it allows you to write C code without actually writing any C code at all. And you can use it to wrap C++ or C or C++ libraries in Python syntax just by using objects, dealing with them. Doesn't matter if it's Python object or C++ object. It looks all the same, feels the same. Okay? Thanks.
Thank you, Stefan. We have time for one question, or maybe two short questions. Are there any questions?
Down here. Yeah, okay, there. Anyway.
Oh, I was wondering, when calling C or C++ code from Cython, what is the level of support for the new standards of C and C++?
For what? For different standards of C++?
C++, 11, so on and so forth.
It depends on your C++ compiler. So Cython doesn't really care. I mean, it can be C++ 11, can be C++ 90 or whatever there is. So just depends on your C++ compiler. Mm-hmm.
I think it generates pure C code, not C++.
Yeah. So the question was, does it generate C code or C++ code? It depends. So it generates C code for almost everything except when you're interacting with C++ objects, in which case you get C++ code for it. Okay. So it knows about operators, for example. So operator plus will translate into A plus B. So you get C++ code for everything that's C++ usage in your Cython code.
Okay, thank you.
Thanks.
Once again.